Okay, before we start talking about integration with partial fraction decomposition, let me talk to you a little bit about some fractions. We all know that if we wanted to combine these three fractions here, we'd need a common denominator. The lowest common denominator here would be the product of the three denominators, x times x plus 3 and x minus 1. And I won't bore you with going through how I got a common denominator and combined them, but let me just show you that at the end, the final result would be this. And notice in the denominator, I actually multiplied my LCD out here. Alright, but here's the question. We've shown that if you combine these three fractions, it would equal this. But what if you were given this right here? Could you then find a way to show that it can be decomposed into these three fractions? Well, if you were asked, think about this. Suppose you were asked to integrate this rational function here. Well, it's probably very difficult to integrate it in this form, but if you could break it up into these fractions, you actually could integrate it term by term. And so that's what we want to do. So let's look at some guidelines here for breaking up or decomposing fractions. First of all, if the degree of the function is not lower than the degree g of x, f of x is the numerator and g of x is the denominator. So I guess I should have made that clear. So suppose you have a fraction where you have f of x is your numerator and g of x is your denominator. Okay, so if the degree of f of x is not lower than the degree of g of x, then just use long division to obtain the proper form. Okay, but let's assume that the degree of the numerator is lower than the degree of the denominator like we had here. So here we can't use long division to simplify that. So let's see what we would do if we had the case that I have here, where the degree of the numerator is not lower than the degree of the denominator. So in there it says express g of x, that's the denominator, right? So express the denominator as a product of linear factors px plus q, or irreducible quadratic factors in the form of ax squared plus bx plus c, and collected repeated factors, so that g of x, the denominator, is a product of different factors of the form px plus q to the m, or the quadratic ax squared plus bx plus c to the n for non-negative integers m and n. And then apply the following rules. Okay, so let's say 3a. For each factor of the form px plus q to the m, assuming m is greater than or equal to 1, the partial fraction decomposition contains a sum of partial fractions of this form. So basically, you're going to have a1, where that's going to be that's a constant, over px plus q, then a2 over px plus q quantity squared, and then so on until you get another constant over px plus q to the m. Now, that's only if this common factor in the numerator has powers, has more than one factor of itself. So if you have px plus q by itself, then you would stop here. But if you have px plus q quantity squared, then you would do the first two terms. And if you had px plus q to the third power, you would do 3 terms, and so forth. And you would do something similar if your factors were quadratic factors in the denominator. So, for instance, here, if we had ax squared plus bx plus c to the n, where n is greater than or equal to 1, then the partial fraction decomposition contains terms like this, where you have a1x plus b1, where a1 and b1 are constants, over ax squared plus bx plus c. And then if this factor occurs to a second power, you would use a second term with ax squared plus bx plus c quantity squared, and so forth. So this makes a lot more sense when you actually see it done. So let me show you how we can break it up here using an example. Okay, so here we have 5x minus 3 over x plus 1 times x minus 3. Now here I went ahead and factored the denominator for you. So rule 1 and 2, they don't really apply here. So we'll go ahead and go to rule 3. And we have no repeated factors. See, this factor, the denominator factored in the x plus 1 to the first power and x minus 3 to the first power. So I'm going to have a constant a1 over x plus 1 and a constant b1 over x minus 3. So I can break this up into some constant over x plus 1 plus some constant over x minus 3. Now, so one way to solve this for those constants is to simply multiply all of the terms by the lowest common denominator. So if you multiply on the left by x plus 1 times x minus 3, then of course everything's going to cancel. And you're just going to get 5x minus 3. Now if you multiply these terms on the right by x plus 1 times x minus 3, for the first term you're going to get the x plus 1's cancel, so you're going to get x minus 3 times a1. And then over here, when you multiply the second term by x plus 1, x minus 3, the x minus 3's cancel, and you're going to get b1 times x plus 1. Now actually you could just say a and b, but anyway, let's go ahead and see what happens here. So over here I have 5x minus 3. Now let's distribute this. If I distribute this, I get a1x minus 3 times a1, and then if I distribute here, I get b1x times b1 plus b1 times 1, which is b1. So I get b1x plus b1. Now, collect your like terms. Notice you have a a1x and a b1x. So if you collect those together, a1x plus b1x, okay, now I don't need this. I wrote that down twice. Okay, so here if I can factor the x out of this, and so I get a1 plus b1 times x here. Okay, and then here I have minus 3a plus b1. Okay, now here's what I want you to realize. The a1 plus b1 is the coefficient of the x term, and that must equal the coefficient of the x term over here, 5. So a1 plus b1 must equal 5. And then the minus 3a1 plus b1, that's your constants. And so the constants minus 3a1 plus b1 must equal the constant here, which is minus 3. So minus 3a1 plus b1 must equal the negative 3. Now, I'm going to let you solve the system. But basically what you do is you solve this system of equations. And when you solve that system of equations, you'll get a1 is 2 and b1 is 3. And now that you know a1 and b1, you can write this fraction 5x minus 3 over x plus 1 times x minus 3 as, remember what I said? It's going to break up into a1 over x plus 1, so that's going to be 2 over x plus 1, and then plus b1 over x minus 3, so since b1 is 3, plus 3 over x minus 3. Okay, so that's how you would solve that one. Okay. Now, this is the same type of problem, but notice if I factor the denominator, it factors into 3 factors, x times x plus 3 times x minus 1. I'll leave you to do the factoring there. Okay, so since I have 3 factors, I can write this as a over the first factor. These are three linear factors. So a over the first linear factor plus b over the second linear factor plus c over the third linear factor. So, I tell you up here you can use a, b, and c rather than a1, b1, and c1. Okay, now, we know that the LCD was x times x plus 3 times x minus 1. So if we multiply this by the LCD, then it'll just cancel the denominators and I'll just get the numerator. Okay. Now if I multiply each one of these fractions over here by the LCD, each time one of the factors will cancel, I'll be left with the other two. So when I multiply the first term, I'll have a times x plus 3 times x minus 1. The second term, I'll have b times x minus 1. If I multiply the third term, I'll get c times x plus 3. Now, I'll leave you to do the algebra here. Let's simplify everything on the right side. Let me see what I can do here. Okay, so I'm going to FOIL x plus 3 times x minus 1, and I'll get x squared plus 2x minus 3. And then distribute x times x minus 1, I'll get x squared minus x. Then distribute x times x plus 3, I get x squared plus 3x. Then I'll distribute the a through each of these, and I'll just show you that that's what I'll get there. And I'll distribute the b through both of those, and I'll get bx squared minus bx. I'll distribute the c through both of those, and I'll get cx squared plus 3cx. Now, let's collect the squared terms together. So I have ax squared plus bx squared plus cx squared. So if I factor out the x squared, that tells me that I have a plus b plus c times x squared. So the coefficient of x squared is a plus b plus c. And then if you go back up here, what's the coefficient of x squared up here? It's 4. So I know that a plus b plus c must equal 4. Now, let's look at your x terms. I have 2ax minus bx plus 3x. So if I factor the x out of these three terms, I get 2a minus b plus 3c times x. So the coefficient of x here is 2a minus b plus 3c, and the coefficient of x on the other side is 13. So that has to equal 13. And then the constants, I actually only get one constant here, the minus 3a. So the minus 3a, that must equal the constant term, negative 9 up here. So minus 3a must be equal to negative 9. Now, you can easily solve for a from this last equation here. And so you get a equals 3. And then you can plug the 3 back into each of these and simplify the equations. And then you can solve the system of equations you get to get b and c. Now, b, I went ahead and solved that. I got b was negative 1, and I got c is 2. And now remember what this broke up into. This broke up into a over x, and since a is 3, that'd be 3 over x. All right, plus b over x plus 3. Well, b is minus 1, so you could do plus minus 1 over x plus 3, or I could just say minus 1 over x plus 3. And then c over x minus 1, and we know that c is 2, so that'd be plus 2 over x minus 1. Okay? So there you go. That's how you can solve those. In other words, write those fractions in a decomposition of partial fractions. Now, the reason we would do this, and I'll show you now, if you'll real quick, I'll show you. Remember that I wrote this fraction as these two terms. And actually, I can integrate these two terms. If you integrate 2 over x plus 1, that's going to be 2 times the natural log of the absolute value of x plus 1. And then if you integrate 3 over x minus 3, that's going to give you 3 times the natural log, absolute value of x minus 3, and then, of course, plus a constant. And then this one, it broke up into these three terms. And again, you can integrate each one of these three terms. And so the idea here is by writing these fractions into a decomposition of several other fractions, we can actually integrate these other fractions. So I'll do some more examples on the next video, but hopefully you saw here the whole reason for going through all this.